So now let's look at centrifugal tension. So in centrifugal tension, what happens is, since the belt moves around two pulleys, so the pulley imparts a centrifugal force onto the belt as soon as the belt comes into contact with the pulley. So we need to take into account the centrifugal tension when we're doing our analysis. So before we begin looking at centrifugal tension, I just want to mention as to how everything is going to be looked at. So what happens is, this is just a general case. So you've got a driving pulley, driven pulley, and around these two pulleys you've got a belt. So what would happen is, let's assume that again we fix the belt at this point. So as the driving pulley rotates clockwise, so this portion of the belt is pulled, so this becomes your tight side and this becomes your slack side. So the maximum tension is always on the tight side. So if we have to take into account centrifugal tension, so the tension on the tight side would be T1 plus Tc, and the tension on the tight side would be T2 plus Tc if and when you're required to take into account the effect of the centrifugal tension. So moving on. So the first thing that we need to look at is the formula for finding our centrifugal tension. So Tc is equals to mv squared, and m is simply the mass of the belt per unit length in kg. So we will find a way to find this mass. So your centrifugal tension Tc is mv squared. So let's look at expressions 10 and expressions 11. When centrifugal tension is taken into account, the total tension in the tight side is Tt1, which is equals to T1 plus Tc. So again, T1 is total tension in the tight side, Tt2 is the total tension in the slack side. So when centrifugal tension is to be taken into account, so the total tension on the tight side is T1 plus Tc, and when centrifugal tension is taken into account, then the total tension on the slack side is Tt2, which is T2 plus Tc. So in previous example we said that we did not mention centrifugal tension at all. So the total tension on the tight side was simply T1 because there was no Tc present, and the total tension on the slack side was simply T2 since Tc was not present. But however, all the problems that we will be looking at from now onwards will have or will include your centrifugal tension. So moving on. So what happens is, the power transmitted is again given by power is equals to Tt1 minus Tt2 into the linear velocity. Once we substitute and simplify, we again simply end up with this expression that your power transmitted by the belt is nothing but T1 minus T2 times your linear velocity. For me, this is the tension ratio that we will be using because we don't want to get confused with this equation. So we'll use the same tension ratio even when centrifugal tension is present. So your tension ratio is T1 over T2 is equals to exponential mu theta. Now the last thing that we need to consider is we need to accept the fact that the maximum tension in the belt will always occur on the tight side. So the maximum tension, the highest tension in the belt will always be on the tight side. And what happens is, since centrifugal tension is present, how do we take into account? And when centrifugal tension is not present, what do we do? So a little consideration will show that the maximum tension in the belt, which is denoted as capital T, so that's your maximum tension, is nothing but equal to the total tension in the tight side of the belt. So this is what we're trying to say. Now if we know the maximum tension in the belt, then equation 14 is very, very important. So what equation 14 says is that the maximum tension, which is capital T, is simply equal to the total tension on the tight side of the belt, and this is also equal to sigma times your cross-sectional area, right? And then this equation can be further simplified into this if and only if we get a flat belt, because B is the width of the belt and T is the thickness of the belt. So if we get a round belt, so your cross-sectional area would be pi d squared upon 4. If you have a V belt, then there would be ways for you to calculate the cross-sectional area of that V belt, or maybe the area of the V belt would be given to you. So now equation 14 what it does is, or what it shows is, that your maximum tension, which is simply capital T, is nothing but the total tension on the tight side of the belt, which is simply equal to sigma I, and I is the cross-sectional area. Now these 2 points are very, very important. So what happens is, from now onwards we will always take into account centrifugal tension. So what happens is, when centrifugal tension is neglected, then the maximum tension, which is same as the total tension on the tight side, is simply equals to T1, because there is no centrifugal tension present. Then when centrifugal tension is considered, then the maximum tension, which is simply equal to the total tension on the tight side, is simply equals to T1 plus Tc. So this is very, very important. So these are very, very important points to remember. So now what happens is, let's look at condition for maximum power transmission. So equation 15 and 16 you just need to remember. For maximum power transmission, your centrifugal tension is just 1/3 your maximum tension. So that's equation 15. So your Tc is simply 1/3 the maximum tension. Here, when the question clearly states that, okay, assume maximum power transmission condition, you don't need to calculate your centrifugal tension using Tc is equals to mv squared. You'll simply use expression 15, which says that your centrifugal tension is 1/3 your maximum tension. And then what happens is, your velocity, we won't use velocity is equals to pi d n upon 60, we'll use equation 16. So your velocity for maximum power transmission would be your maximum tension T divided by 3m whole thing square root. M again is the mass of the belt per unit length, right? So M is again the mass of the belt per unit length, and again for maximum power transmission condition, Tc is equals to 1/3 your maximum tension. So now let's look at example 2. So a leather belt which is 9 mm by 250 mm in dimension is driven by cast iron pulley which is 900 mm in diameter, and the pulley rotates at a speed of 336 revolutions per minute. The rep angle is given as 120 degrees, right? And the stress in the belt is 2 megapascal. Find the power capacity of the belt. The density of the belt is given as 980 kg per meter cube, and the coefficient of friction is given as 0.35. So the first thing that I would do here is highlight all the quantitative information that is given to you. So the dimension of the belt is as such, the diameter of the pulley is 900, speed at which the pulley is rotating is 336 revolutions per minute, the rep angle, the lap angle is 120 degrees, the maximum stress is 2 megapascal, right? Density is given as 980 kg per meter cube, and finally the coefficient of friction is 0.35. So let's start looking at this problem step by step. So the first thing is, we can calculate our linear velocity. So velocity is pi d n upon 60. Before we start looking at example 2, just take this note down. So in this question we will take into account the effect of centrifugal tension. So example 2 will include the effect of centrifugal tension, which is your Tc. So substituting for diameter of 900 mm, which is 0.9 meters, speed was given as 336 revolutions per minute. So we end up with a value of 15.83 meter per second for our linear velocity. Now mass per unit length can be simply calculated as, we know the density is mass upon volume from fluid mechanics. So density is mass upon volume even from solid mechanics or our basic physics. So mass is simply density times our volume. So density and volume is what? Cross-sectional area times the length or the height of that particular object that we're looking at. So what we have is, we know the dimensions of the belt, and what we do is, mass over here is per unit length. So this length will be simply replaced by 1 meter. So density is 980, width of the belt was 0.25 meters, the thickness of the belt was 9 mm, converting it to meters, and length, we assume the length to be 1 meter. So what we do is, we end up with the value of mass to be 2.205 kg. So moving on, the maximum tension, which is nothing but equal to the total tension on the tight side, is simply equals to sigma times A. And we know that since it's a flat belt, so the cross sectional area will be simply width times the thickness. So sigma times B times T. So our stress was given as 2 megapascal times the width times the thickness of the belt. We get a value of our maximum tension to be 4500 newtons. Now what we do is we can also calculate our centrifugal tension TC, which is equals to mv squared. Mass we calculated earlier from over here to be 2.205 kg times the velocity 15.83. So substituting all these values into this formula, we get our centrifugal tension to be 552.55 Newton. Remembering that your maximum tension is nothing but the total tension on the tight side, which is TT1 is equals to T1 plus TC. Let's make T1 the subject of the formula over here. So what we have is T1 is equals to TT1 minus TC. So 4500, which was our maximum tension, minus our centrifugal tension, we get our T1 to be 3947.45 Newton. So I hope you follow up till here. Now what happens is the rep angle was given as 120 degrees. So 120 over 180 times pi. We get our theta, our rep angle in radians is 2.09. The tension ratio T1 over T2 is equal to exponential mu theta. So exponential coefficient of friction was given as 0.35. Rep angle converted to radians is 2.09. So we get our tension ratio as T1 over T2 as 2.08. And since we know that our T1 was 3947.45 Newton, so we can always find T2. So therefore T2 was T1 over 2.08. So which equates to 1897.81 Newton. And then power is nothing but T1 minus T2 into linear velocity. So T1 was 3947.45 minus T2 times your linear velocity. So the power that can be transmitted by this belt, taking into account your centrifugal tension, is basically 32.45 kilowatt. So once more, this question is not complicated. So the first thing is calculate your linear velocity. Mass is simply given as rho times volume. So density times your volume, which is cross sectional area, times the length. Length we assume to be 1 meter per unit length of the belt. So we get 2.205 kg. Our tension, maximum tension is total tension on the tight side. So sigma A, we get a value of 4500. Centrifugal tension we can calculate using this formula. So we get 552.55. Then this step is the only step that is new to us, which is very, very critical. So your maximum tension T is nothing but the total tension on your tight side, and the total tension on the tight side is T1 plus TC. So we know our total tension on the tight side is 4500. We know our TC. Let's solve for T1. So we get particular value of 3947.45. Using the tension ratio, we can find T2. Keep in mind that we need to convert the rep angle into radians. So we get our T2 to be 1897.81 Newton. So substituting, we get a value of 32.45 kilowatt.